So I'm now going to talk about how we can sample from some simple distributions in Matlab using some of the functions provided by Matlab. So first of all, why do we want to occasionally do this kind of thing? Well, we might want to generate some data and sample from distributions for various different reasons. One reason could be that we want to make a random decision, or we want to make a decision with a certain probability, and we can do that using the rand function. And this kind of decision, 20% of the time maybe we'll want to do exploration, or 80% of the time we want to take advantage of something. That's a typical kind of thing that we need to do in reinforcement learning algorithms. It may be that we want to generate some test data with known characteristics such that we can test a classifier. So we might want to have a couple of basically clusters of data that are separated in terms of their mean values, but have got some very, very low probability overlap, which we can put in because we're generating something, let's say, from a Gaussian distribution with a large or sufficiently large standard deviation. So occasionally data points will actually impinge upon, where the centers of the other clusters are. Could also be we want to test a regression algorithm. So we want to, let's say, fit a line to some noisy data. And it's easy to generate the deterministic part, but then we can use one of these random sampling algorithms in order to actually give us some random values that we can add in and make things noisy. In fact, making things noisy is something that we might want to do in general, simply because when we're normally building systems with Matlab and running simulations, quite a lot of the time we'll be doing it in a very noise-free, deterministic way. But as soon as we stumble on the real world and have to deal with doing real machine learning problems, we find that there's a lot of noise in the signals that we're playing around with. So it's good to be able to corrupt artificial data sets, or even real data sets, and corrupt them even more by adding in noise. And to do that, we need to sample from distributions to get random values. So Matlab has got two functions that are particularly useful for this kind of thing. One is rand, which will sample from a uniform distribution between 0 and 1, and rand n, which will sample from a Gaussian distribution of mean 0 and standard deviation 1. So let's think about sampling from a uniform distribution. It's so easy. We just call rand. If you call rand with two parameters, n, m, then you'll get basically a matrix of size n, m full of these random values, which basically have been sampled between the interval of 0 and 1, and it returns obviously a double value. So normally, if we looked at the distribution then for this sampling function, like I said, it's basically a probability density which is uniform between 0 and 1. So if we actually plotted a little graph of what this density looks like, it would look like this. It's 0 until we get to 0. It then shoots up to a density of 1. It's then completely flat until we get to a sample value of 1, and it comes down again. Now, obviously, the mean of this of values coming from this, if we sampled lots and lots of values from this distribution, hopefully you'd be able to see that if we took the mean, then just looking at this graph, you can see the mean's going to end up being about tending towards a half, right? It's going to be the central part of this. Now, quite often we want a zero mean value, so we can start mucking about with things in terms of means and ranges and stuff. So the easiest thing to do to make this then in terms to a zero mean distribution is for every time we take a sample, we subtract 0.5 from it. Right, so we take 0.5 off. This gives us a zero mean distribution, and if we plotted that out, what does this probability density look like? This is what it would look like. We're now sampling from a distribution between effectively minus 0.5 and 0.5, and mean will be the mean will be 0 in the center. So it's easy to shift the mean just by subtracting the value. We can also scale the values in order to get a larger range or a smaller range, and we can then also add on a mean value if we want to have anything other than 0. It's quite easy to do. So let's think about that in a little bit more general terms. Let's say we want to generate samples from a distribution which is uniform between the values of y lower, the lower value, and y upper. First of all, we need to specify the range and the mean in order to be able to scale our rand values, and also we need to know the mean that we want in order to add that on. So let's think about what the range of this is. Well, if you've got an upper value and a lower value on our distribution, then obviously the overall range is going to be the upper value take away the lower value, right? So that's just the difference. It's the distance between the two. And the mean is just going to be the average of the two, right? So it's going to be, using the standard way of calculating a mean, it's going to be the lower value plus the upper value. And we're not actually doing integration here. We could actually do it by a bit more of a rigorous approach, but we're just looking at the upper and the lower values. So we've got the range, y upper minus y lower. We've got the mean value, y upper plus y lower divided by 2. Therefore, in order to actually now have a sample which appears to have been drawn from this uniform distribution from y lower to y upper, all we have to do is we get our corrected rand value with a 0 mean. So it's then rand minus 0.5. That gives us our distribution between minus 0.5 and 0.5. It's got a range of 1 normally. So what we all have to do is we have to multiply it by the range we want. So we multiply, first of all, the value of the sample by that. And then we need to add on the additional mean value that we actually want to do. So we add on the mean value that we've calculated. And that gives us a final expression. You can just substitute this range and this mean value into this expression here. We see then, and we just get a scaling factor multiplied by the sample that we get from rand that we've taken away 0.5 from, and then we add on the mean value that we want. One really useful thing about using rand is we can use it to make a decision with a certain probability. The simplest decision to make is going to be a binary one. We either do one thing or we do something else. And if we just call rand on its own, it just gives us a single sample. Now everything in Matlab is a matrix, so actually a single sample is a value, but it's actually a 1-by-1 matrix. But if you just call rand on its own, it will return a single value. It's the same as calling rand with values of open bracket 1, comma 1, close bracket, because it's a 1-by-1 matrix. So this is going to return a value sampled uniformly from the interval of 0.1. So let's think about what this range looks like. First of all, we've got the range now. This is our probability distribution again. It's got a density of 1 when we go from a sample value of 0 all the way along to sample value of 1, and then it comes down to 0 again. Now what we want to do is, let's say we want to pick something with a certain probability. Let's say we're going to now look at a sample value of v, which is between 0 and 1. And drawing it on this diagram, what you see is we've now split up this density into two parts. We've got the lower region, where the value that the sample we get is between 0 and v, and that corresponds to this red area, and the upper part is when the sample value that we get is between v and 1. So looking at this picture, you can see if we actually get a value between 0 and v, this corresponds to one probability, right? It's the probability that the value is going to be less than v, and it corresponds to the area here shown in red. And if the value that we get is v or bigger, that corresponds to this blue area here. Overall, of course, the probability's got to be 1, right? The chances of we've got to get a value between 0 and 1 because we're sampling between 0 and 1. And it's always important to remember the area under a probability distribution is always going to be 1. That's by definition got to be the case. And in this case, therefore, the probability that we're going to get between 0 and v is going to be v, right? This area corresponds to v. So v is the probability, and it's something that is greater than equal to 0 and less than equal to 1, right? So it's got to be something which is less than 1, and it's got to be something more than which is more than 0. So what can we do? Imagine we want to now sample from from this uniform distribution using RAND, and we want to take either action A or action B. Let's say we want to take action B with probability A. What do we have to do? Well, it's actually really simple. First of all, if we take action A with probability PA, then we're taking action B with probability PB, which is 1 minus PA, right? So the probability of one thing happening, or the other thing happening, has got to be 1 overall. So we can say that if A happens with probability A, then B happens with probability 1 minus probability A. So let's think about the code to make decision action A with probability A. What we do is we just say we sample from our random distribution, our uniform distribution, and if the value we get back is, in fact you could say less than equal to, but I'm just saying if probability is less than PA, then we take action A, right? Otherwise we take action B, and that's basically it, right? It's that simple. If the probability that it's going to be the value is going to be less, the value that we get is less than PA, corresponds to this blue bit on the red bit here. That's going to be this area here, and the chances of it being more is going to be this blue bit here. So that's basically what we're up to. So it's actually quite simple to use this. Now in practice you could split up this region even more into multiple regions if you wanted to do that, and if you wanted to make 3 decisions, A, B or C, you just have to say which region is it in, is the value of RAND between certain different values in order to make certain, in this case, mutually exclusive decisions. Let's now think about the RAND N function. Like I said, it's very easy to draw from Gaussian distributions using Matlab because they've given you the RAND N function, and what this does is it basically lets you draw samples. If we say 1, 1, we'll just get a single value, a 1 by 1 matrix, but if you could have you could have 100 by 100 and you get 100 by 100 values in the matrix. Important thing to note is the mean of the distribution it's sampling from is 0, and the standard deviation is 1, right? So if we plotted that out, it would maybe the density would look something like this. The standard deviation values are plus or minus 1 around the center point of 0. We can easily change then again, where it appears that these samples are coming from, because all we have to do is to scale again the samples we get. In fact, we scale them by the standard deviation, in this case, that we want, and then we add on the mean mu, right? So if we want something now that looks as it's been sampled from a distribution of arbitrary standard deviation sigma, what we do is we get our sample value, we multiply the value we get by sigma, and then we add on the mean, right? Bear in mind that in the one-dimensional case, sigma is the square root of the variance, right? That's something we have to bear in mind. So if we now look at what this distribution would look like when we plot it out, what we've done now is we've said now we've actually got a slightly modified probability density function. Now the actual mean is mu, and of course therefore the standard deviation is going to be mu plus sigma and mu minus sigma. Those are going to be the ranges that we have. We will talk more about Gaussians a bit later on. Now here's a question. This is something out of an exam. If we use RAND n, 1, to draw n samples for a 1D distribution, and we get x1, and use it again to get n samples for a distribution, and we end up with x2, and then build a 2D vector x, where x1 is one of the features and x2 is one of the other features. It's not very clear in that question. What does the covariance of this data set look like? So we're jumping the gun a bit here by jumping into covariance matrices, but let's think about what that means. Well, basically what we're saying is we're sampling from to get feature 1, we're sampling from this Gaussian, And then to get feature 2, we're also sampling from this Gaussian, but we're doing these things independently. So that means that feature 1 and feature 2 are completely independent. And if they're completely independent, what it means is there's no covariance between them. So if we actually calculated the covariance matrix of this overall data set we end up with, it's going to have no covariance terms. However, if we look at the variance of data set x1 and the variance of data set x2, they're going to correspond to what the variance is that where we're drawing from, which is what's the variance assumed to be for rand n. And well, we know the standard deviation is assumed to be 1, so the variance is assumed to be 1. Therefore, for feature x1, the variance is going to be 1, and for feature x2, the variance is going to be 2. Now, we can basically capture all that information by writing it into the covariance matrix. And the covariance matrix, effectively, for a 2 by 2 system like this one, so for a 2-dimensional vector, the first term here, the 1, 1 term, that's going to be representing the variance of x1. The 1, 2 term here, that's going to be representing the covariance between x1 and x2, and we know that's 0. In the second row, we see that this term here, the 2.1 term, this is going to be the covariance again between x1 and x2, and we know that's 0. And this final value here, this 2,2 term, that's going to correspond to the variance of feature 2, and again we know that is going to be 1, right? So this leading diagonal represents the actual variances of the features, and the one going in the opposite direction represents, in this case, their covariances, which happen to be 0. So the covariances are basically 0 in this particular example, and that's because we've independently sampled from rand n to get the first feature, and then we've done it again independently to get the second feature. So there's no covariance, there's no correlation, no relationship between what we do with feature 1 and what we do with feature 2. Now, in general, we may well want some data where that's not the case. We might want something with some covariance. So, if I say something about if I look at feature 1, it says something also about what's feature 2 doing as well, and that comes back to our plots of scatter plots, right? If x says something about y, that means you have this general trend for things to be on a diagonal line. If x says nothing about y, then they're completely independent, and there's no relation between the two features. So how can now we generate, in a multidimensional case, a system where we can specify the covariance matrix and the mean vector? Well, again, like we said before, if there's 0 covariance and the features are independent, it's easy to generate data in which there is 0 covariance. All we have to do is sample for feature 1 and then independently sample for feature 2. Right? So all we have to do is, in this case, we sample using rand n for feature 1, and we're actually multiplying it by something with a variance of 10. So we're scaling this with a standard deviation of the square root of 10. And then we're independently generating data for feature 2, and in this case we are basically multiplying it with something with a variance of 1. So we've got feature 1, in this case, is going to be random Gaussian data with variance of 10, and feature 2 is going to be random Gaussian sampled data with variance of 1. Now, in this particular case, again, these are going to be independent, but we're choosing an example now where the feature 1 and the feature 2 haven't got the same variance, right? And if we plot these out, we'll see something slightly different. Again, you do need to say axis equal in order to make sure that the axes actually are the same scale. Otherwise, you won't see some of these effects because it'll automatically scale and everything will look the same all the time, right? So if we actually plot that out, what we see now is if we look at this is how I'd represent the covariance. There is no covariance term here. There's no covariance term here, but the X data has got a variance of 10, and the Y data has got a variance of 1. So what it means is that the variance of 10 on the X data means there's going to be a big spread along the X-axis, and that's what you see here, right? Look, notice that we've effectively almost got the same scaling anyway, not quite maybe. What we've got here is a big spread in the X, which is what you'd expect because you've got a big variance here, and we've got a much smaller spread in the Y because we've got a variance of 1. Right? So this is the effect that you get. If they're plotted roughly on the same scale, what you see therefore is rather than having a nice spherical cluster of points, you've got this ellipse. But the important thing is this ellipse, the principal axes of this ellipse actually line up with the axes of the X and the Y, right? So you haven't got anything at an angle, you've got no diagonal effect. Don't forget, the diagonal effect basically means that things have got some sort of correlation. So what this is, look, when you look at this, you can say, well, we can see, first of all, that there's more spread in X than there is in Y, but it's not along a diagonal, so we know that X and Y is independent. Okay? If we generate that data, right, like this, and then we actually reanalyze using COV, we can actually look at what Matlab thinks given the data that we've got. What does it think that the covariance matrix looks like? And we can see it sort of thinks that the leading diagonal that's almost 10 and 1, which is about right. It's almost got 0 covariance values. You're going to have a little tiny bit off that. And the reason for that is because we've got to analyze a finite number of samples. As the number of samples went to infinity, we'd get back to hopefully what we said we were sampling from. This also illustrates the fact that though it's actually, you know, difficult to actually estimate parameters from real data unless you've got lots and lots of real data. Let's just flip round now the way we put the variances in. Let's put X now as a variance of 1 and Y as a variance of 10. So in this case we see that the X doesn't basically vary as much. The spread is it's basically the spread is now quite small along X of just 1, and the spread along Y now instead is larger because it's now got a variance of 10. Again, you can then analyze the, you know, I think I'm generating 10, 100,000, maybe, yeah, so many points. Doing the analysis, again, you can see that you can sort of kind of, you know, if we generate this data and analyze it with COV, you can see that we end up getting almost back to what we started with, but again you're going to be slightly off because you need an infinite amount of data in order to actually ever get back to where you started. Now, first of all, I said you know, we can look at these plots and we can say, because they line up against the axes, the principal axis of the ellipse line up with the axes, we can say there's nothing along any diagonal. There's not a tendency for things to be on a diagonal. Therefore, we know, looking at this plot, it looks like things are pretty independent between the two features. How can we actually make them not independent? And what will that represent? Well, you can think about what would it have to look like, and you basically want to have them along a kind of a diagonal. So how can we get this to have something along a diagonal? And basically what we can do is we can somehow rotate this system. If we get the data and we can rotate it with regard to X and Y, then we can generate data which has got this correlation, which has got this dependency, which has got this covariance. So let's have a go at that. So some of you have done rotation matrices in robotics. So, and we know that we can always generally rotate a data point, in this case by theta, by multiplying it by a rotation transformation. So if you've got our X and Y data point, we can multiply this by a transformation matrix, which corresponds to, in this case, to a rotation, and we'll get new data points. So what I'm going to do here is I'm just going to say let's build a rotation matrix. It's quite easy to do in Matlab. And then what we're going to do is we're going to rotate all our data points, in this case by 35 degrees. The rotation matrix is going to look something like this for that particular example. We're going to multiply each X and Y vector that we've got, just got previously, by this rotation matrix in order to basically move them away from off alignment with the axes. So we can do that. So we take our nice matrix with our covariance matrix that we had before. We generate the data. Again, we can just check that we can get back to the covariance or nearly. Now what we're going to do is we're going to rotate it by multiplying all these data points that we've got here. We multiply them by our rotation matrix, and we find it then actually moves how the spread appears on the plot, because now it's no longer aligning with the principal axes, right? So the X is now showing a strong trend on affecting Y, because we've actually got this, we've put this dependency in. And if we now analyze that, right, if we actually analyze that, what we'll see is now we've got, in fact, we've reduced the variance terms somewhat, or that one's, at least that one's gone down from 10, it's actually gone down to 7. This one's gone up. But the important thing to note is now we've got covariance in the system as well, right? So X and Y are now no longer actually independent. And this is just an example showing you, right, that we can, you know, when things start lining up along the diagonal, or have a diagonal component, that means Y depends on X. In this case, when it was independent, Y does not depend on X, so that's why they line up along the principal axes of X and Y, and now basically we've got this diagonal component. Now, generally speaking, we don't want to just multiply by a rotation matrix, because that was just to show you that you can do that. Generally speaking, what we want to do is we want to say, I want to generate some multidimensional Gaussian data, and I want the data to have a mean of some mean vector, and also I want a covariance to, let's say, have a covariance matrix K. So how do we deal with that? So again, just like we did in the one-dimensional case, we need to scale it, you know? We need to transform it by multiplying by something which kind of relates to the standard deviation, and then we need to add on the mean. In this case, the scaling is a transformation matrix relating to some aspect of, if you like, the standard deviation, and the mean is going to be a vector. Now, we can't just take the square root of K, right, because K is a matrix, but what we can do is we can say, we can represent K as equal to A transpose times A and solve for A, right? So that's effectively the matrix equivalent of doing a square root. And this can be achieved using Cholesky decomposition. And the way you do that is you call the CHOL, the CHOL command, basically. And what it'll do, it'll decompose K into A transpose A. And then what we're going to do, you just have to be a little bit careful. Let's just go through the code and just show exactly what I'm doing here. I'm just setting a number of samples, 10,000. I'm setting my mean vector to 0 because we're not looking particularly at mean at this stage. I've specified the K that we actually got last time when we actually did the analysis again. We've got 4, 4.2, 4.27. That's the variance of feature 1 is 4. Variance of feature 2 is 7, and the covariance terms are 4.2. And then I'm decomposing K using this CHOL command. I'm generating some uncorrelated data, and then what I'm doing is I'm multiplying the uncorrelated data by my transformation matrix here. We have to transpose it in order to get the thing to actually do the right dimensionality multiplication. And then what I do is I add on the mean, and then I'm just plotting it, right? And that's what we end up with. So this time what I've done is, you know, rather than using rotating it by 35 degrees, what I'm saying is we want to specify generally what the covariance matrix is that we want. We can then decompose it. We can then multiply the data points which are uncorrelated by this transformation, and then we can add on the mean, and then we end up hopefully getting back, after you've got to enough samples, if you reanalyze all this data again, you should get back to what you started with. In fact, that's a very good tip. When you are doing things and you have the opportunity of reanalyzing, it's a good way of checking that you haven't made any mistakes. So that's one way of changing the, if you like, the probability distribution characteristics. We can scale means, and we can add on variances change. Well, we can see, we can other way round. We can scale variances and we can add on means. There's other ways as well of getting to arbitrary distributions by doing transformations, and one of these is using the idea of using cumulative distributions. I'm not going to really go through this as a method as such, it's just I want to explain the technique as such, right? So imagine we want to sample from an arbitrary distribution, and we will come back to this in rejection sampling in a much more practical way. But imagine, how could we generally do that? So imagine we've got this two-dimensional, well, we've got this, not the two-dimensional, we've got a one-dimensional uniform distribution, which is actually built of two parts in this case. It's built of two uniform parts. We've got the first part, which is between 0 and 0.5, and the second part, which is built from 0.5 to 1. We could actually build this up by adding together values from two random uniform distributions, but let's think about more of a general issue here. If I said that's something that we want to actually sample from, and how could we do that in general? And secondly, what does exactly that mean in terms of the samples? Well, if we look at this distribution, we see the probability density for the first region from 0.0 to 0.5 is actually about half what it is in the second region. That means if I sample from this distribution, I'm going to get, on average, twice as many samples coming out of the blue part from 0.5 to 1 as I'm going to get coming out of the red part, because the probability density is twice as much, right? So we get twice as many samples from this as we get from that. So what does that mean? Right, so let's think about what the cumulative distribution of this then will look like. Well, obviously, because this is half as many as this, the cumulative values of the probability will integrate slower as we move along here. So basically, cumulative distribution is just saying, let's look at the area under the density as we move through value. So as we move along, starting here, then obviously the area is 0, but as we move what's to the left of the point that I'm at, we can, if we work out what the area to the left of the point I'm at it is, as we move along, obviously it goes up linearly, right, corresponding to the area under this red bit here to the left. But we see, because this density is half of what this is, it goes up a lot slower for the first half of the value than for the second half, because here we've got twice the density, right? So this is going up at one gradient, and this is going up at twice the gradient. So we can see immediately on this that the chances are we're not going to get as many values from this bit as we get from that bit here. In fact, we're going to get effectively twice as many from the blue bit as we get from the red bit. So we could actually use this kind of density now to actually map back in order to sample from this distribution that we've got. So if we calculate this cumulative density, the way it would work would be, what we do is we say, we're now going to sample between 0 and 1 using, let's say, rand, but then we're going to use the value we get here, right? We're going to sample from a value, and we're going to use where it lines up on the cumulative density, and in order to map or to scale the value. So what's going to happen here then is we're going to say, if we get a value between 0 and a third, in fact, it's going to be, a 0 and a third is going to map between 0 and 0.5, right? So we're going to scale the value in such a way that if something is between 0 and a third, that represents this point to this point, we map from 0 to 0.5. But what we see is that for the first third of the values, then we're mapping 0 to 0.33 recurring, if you like. We're mapping those to 0 to 0.5. But, and in this particular example, I'm just saying, imagine there was just 2 points there, or 3 points, 1, 2, 3. We just get 3 samples in there. Now, interestingly, because now this point here starts at 0.33 recurring all the way up to 1 here, that we've got a much larger range now, which is going to map onto the second part of the probability distribution. So when we start sampling and samples land between a third and 1, they're going to map to the blue region, right? They're going to map to the blue region, which means in this particular example, we're going to get twice as many samples landing here as we get landing here. So just by using this, if you like it, we're using the, this transformation, saying, how can we map these things together in order to map to, from 0 to a third to a third to 1, by using this relationship relating to the inverse cumulative density, we can actually scale things appropriately and thereby lead to the actual distribution that we want. And this is just using an example from a step of point, a two-part uniform distribution. Obviously this could be something completely arbitrary, in which case you'd need a much more arbitrary cumulative density that corresponded to it.